must realize that an alcohol is very similar to water. Maybe by now you know that water looks like this, it's bent. Well, alcohol looks like this, right? ROH, right? They're almost the same, right? If this is small, then it looks a lot the same, right? So these are small R's. Water looks a lot like alcohol. In fact, you can say they're very similar because when you, I don't know if you drink, but if you put ice, let's say you say vodka on the rocks, what does that mean? That means vodka with ice, right? What happens to the ice eventually? It melts, right? Ice is water, right? So when you melt that ice, you see like 2 layers in there in that cup? No, it all is one, right? So that means that the water is soluble with the alcohol and the alcohol is soluble with the water. So like dissolves like. They must be very similar. Got it? So water is similar to alcohol. So if water adds to the aldehyde or the ketone, what do you think the alcohol is going to do? The same thing. Okay? So in this case, the alcohol is the nucleophile, not water. Now what's the big difference? The big difference is that these guys on the screen are the products, and they are stable. Unlike this thing, the diol, that's not stable. Okay? So this one is very stable. So how do you get these? You add 1 mole of alcohol to an aldehyde or ketone, and what do you get? The first product is this guy, hemiacetal. Now, if you read here, what does it say? The hemiacetal, even though it's made, it's what? Unstable also. Well, we're not surprised, right? Because water gives me something pretty unstable. So the first leg of this will give you this unstable hemiacetal. So what do unstable things want to do? They want to react, right? So the second product, the acetal, comes by this guy being made first by adding aldehyde ketone with 1 mole of alcohol. This is where the alcohol goes, OR. You see? ROH, RO, and the H is gone. So we make this first with 1 mole of alcohol, and then we add a second mole of alcohol. So to get this acetal, how many alcohols do you need? 2, right? And you see on the product, here's one of them, here's the other guy, right? ROH, right? That's where the alcohols went. So in order to get acetal, you need 2 alcohols. In order to get hemi, you need 1. However, realize the hemi is what? Unstable, right? So now we have to ask her, why is this thing so unstable? Why was this one not even in, she said, yeah, it's made, but don't even bother, who cares about it, because we can't isolate it, right? It's not really something that is useful to us. Why do you think, what is one thing that these unstable things seem to have? Look at, this one is stable, by the way. The acetal is very stable. But this one is not, and this one's even worse, this gem diol. See this guy? What do you see in common with the unstable ones that's not present in the stable ones? Here's the very, very, very unstable. You take that look. Then you go to the kind of unstable, and then the super stable. What's missing in the super stable?
The OH.
OH, that's right. So why does the presence of the OH make everything so unstable? What can OH do? Well, what if there's acid in the mix? That means acid makes H pluses, right? H plus protons. What can H plus do with OH? Well, the OH has electrons, doesn't it?
Yeah.
So what's the electron's charge?
Negative.
And what's H plus charge? Plus. So what do we do with plus and minus?
Combine.
Combine them, attack, right? Make a bond. So this O with the electrons can react with an H and pick up an H. If I add an H to this O, what will I make? Kind of?
Water.
Water. And what do we know about water? Great leaving group. That's correct. So if things are leaving, that means that we're promoting reactions. You know what I mean? So that means that this one is unstable. So the fact that you have this OH allows you to make the potentially great leaving group, which is water. And water, once water leaves, that means a reaction is taking place. Now here, we don't have the situation, we don't have any OH. So that's why this one is more stable than these other two. So that's why these are big roles in sugar chemistry, right? All right. Now, we're gonna do this mechanism in 18.4. And then we're gonna figure out, before we do that, we're gonna look at these things that we're gonna, when we do the mechanism, we have to keep this in mind. Alright, so in nucleophilic additions, that's what we're doing, right? It's either redox, it's your chocolate or vanilla, right? This is a very simple, carve-out. I got chocolate and I got vanilla, that's it. So I got redox reactions for aldehydes and ketones, or nucleophilic addition reaction. Those are your choices, nothing else, okay? So here, sp2 will become sp3 at the end. This is one thing to keep in mind. When you do these mechanisms, a double bond will disappear. Everything will be single bond at the end. That's what that means. sp2 becomes sp3. What else do we see? The reactions usually require a catalyst. What else? What's a catalyst? In this case, the catalyst is usually acid, H+. A nucleophile, whether it be negative or neutral, is always required. Of course it's required because we're doing a nucleophilic addition, so we require a nucleophile. Next, acid is used at the end of the reaction to end cap the negative charge. So we basically cannot leave it negative. Anytime you can't leave a reaction negative or positive at the end, it has to be neutral, right? All right. So if we keep these 4 stars in mind, if you have a book, you take a look at 18.4. I'm going to do just one of these on the board. Acetal and ketal are the same thing. We used to use the word ketal. When I was in your shoes, we use both words, but most of the time we don't see ketal anymore. They are, all that means is acetal used to be starting from aldehyde, ketal used to be starting from ketone. But now everybody just calls it acetal, for whether aldehyde or ketone. It's just become the word. Now what is this thing, acetal or ketal? It's this, the one that has no OH, okay? Now, in this case, when you look at this acetal, you know it must have come from an aldehyde, right? Because you see this H? That is attached to this carbon that does all the changing, that used to be an aldehyde. If I see an R here, then I know it came from a ketone. Got it? All right. So let's do a mechanism instinctively, because I don't even have my notes. So you should be able, maybe not right now, but by next week for sure, you have to know how to be able to do what I'm doing now, okay? So I'm gonna take you step by step. It's called mechanism, right? So the first step for this, so let's call it reactions of alcohols, right? With aldehydes or ketones. Right? So another way to say that is acetal formation. Acetal formation. Okay, and we know what acetal is, right? The acetal is, yes, Leon.
What's after ROH? Is that like
ROH is alcohols.
no, like what's that's after ROH?
This?
No.
This?
Yeah.
With.
Oh.
W, it's a W. With aldehydes or ketones. Got it? So what are we making? We're making this. How are we getting there? We make this first, then we go to this. Okay, so at the end, I have to end up with this. So the first step is we have an aldehyde or a ketone. We react with one alcohol. And we end up with hemiacetal. Right? HA Then I'm gonna take this and I'm gonna react with a second alcohol. And usually it's the same alcohol, okay? And then I'm gonna end up with acetal. Okay, there you go.
So does it matter which type of alcohol, or it can be primary, secondary?
It doesn't really matter. Usually the smaller ones work best because there are no stereochemicals, right? We've known that. But there's no limitation, there's no restriction like we have with Corey-Howes, you know, with the Gilman reactions and things like that. It's not restricted like that. But you have to realize that the bigger the thing is, the longer it's going to take to react. All right, so let's take a really simple aldehyde. So this, since you're experts in naming things already for the test on Thursday, what's the name of this one? IUPAC Cruise. Oh, you didn't do this, right? You didn't eat this, right? Sorry. Well, this is for next week, right? IUPAC is longest carbon chain. What's the longest carbon chain?
Atom.
S, right? 2. So this is called ethanal, right? The ending is always AL for IUPAC or acetaldehyde, right? Those are the names for this guy. So this is a very simple aldehyde. Now I'm going to pick another simple alcohol. So let's do methanol. Okay, and what do I need to get this going?
Catalyst.
Catalyst, right. So I need a catalyst. Usually my catalyst is going to be H+. That's an acid catalyst. Now you notice I use the arrows forward and back. These are equilibrium reactions. That means that we can go forward or backwards. Okay, all right, so let's take a look. This is what I'm about to talk about now. It's a concept that's going to occur in chapter 20 as well. So remember, oh yeah, I should do that already. We recognize that there's pull from that oxygen, right? Very electronegative is pulling those 4 electrons closer to it. That makes these electrons that are hanging out in the double bond closer to O. That makes this O slightly negative, correct? And that makes this carbon slightly positive, correct? So right away we have a plus and a minus in the molecule, right? Now I have this nucleophile, right? It has 2 electrons here, 2 electrons here. Definitely these negative electrons are going to be very attracted to that positive charge, okay? Now, if you want them to be even more attracted, that doesn't hurt, right? That's what the catalyst does. It makes this carbon even more attractive to the alcohol. How? Well, the first step is the H+ from the catalyst is hanging around, and you see these electrons on oxygen, those electrons are going to pick up that hydrogen, okay? So if I pick up this hydrogen, I attack the hydrogen, I make a bond with the hydrogen, right? So really, this is going to change, right? It's going to become CH3, carbon H here, double bond. I have 2 electrons I didn't touch, but these 2 electrons over here, they made a bond with the new H. So let's stick that H here, and there's my new bond. Now, O loves to have 2 bonds, not 3. Right now it has how many? 3. It used to have 4 electrons all by itself. Now it only has 2, and it's sharing 2. So it kind of lost ownership, didn't it? Lost some ownership. So what do we say when we lose electrons? We become positive, right? So the O becomes positive, right? Now, if the O is positive, what do you think about that situation for O? Good or bad?
Bad.
Bad. So what's O going to say? Give me electrons. Somebody give me electrons. If you think it pulled the electrons close to it before, now it's really going to pull those electrons. So there's electrons that are going to be pushed back right on that O. That makes this carbon even more positive, right? Can you see that the positive charge is gonna get bigger here? Because the O is very unhappy being positive, right? So if you think that the O was pulling before, it's really pulling on those double bonds now. So that makes this positive, slightly positive, become almost super positive. Does everybody see what just happened? All right. And is this a better thing for my reaction? I want to attract nucleophiles. Is this going to help me or hurt me? Help me, right? Because if I'm a nucleophile, I'm negative, right? I have electrons, so this is even more attractive now. You follow? So what have we really done? This is called activating the carbonyl. Now, an aldehyde doesn't really need to be activated. It's a very reactive little molecule. But a ketone is a very lazy little molecule, right? So maybe a ketone with its carbonyl can be activated this way too, and that is true. Any unreactive carbonyl will be activated by adding a hydrogen. Okay, so we will do this in chapter 20. We have lazy ester, we have lazy amides, we have lazy carboxylic acids. We always activate the carbonyl. So in chapter 20, to activate the carbonyl, what are you going to do? You're going to add an H plus to the carbonyl. That's what you're doing. Okay, so now you understand that this is superactive now. It's superactive, perfect to react with this. So what's the next step? This is going to attack here. Now, that makes this carbon have how many bonds? 5, right? So we have to kick 2 out, right? Can't have 5 bonds. So who's going to go where? These electrons got to move, right? Out of there. Because we can accommodate 5 bonds, right? So at one point, after this attack happens, we have CH3, COH, and then we have the 2 that just came on board versus the 2 that were already there. Right? So this plus is now full of electrons, so this plus is going to go away. So now we have this. Then we have this H was already there, so leave it alone. And now the oxygen has attacked the carbonyl, so the oxygen is attached, right? This is my new bond, right? Then who's attached to the oxygen? Well, I use these 2, right, to make the bond here, but I still have 2 on there, an H and a CH3. Does everybody see what that looks like? Now, that oxygen, what do you think of the oxygen? Well, it used to have 4, now it only has 2. So lost ownership, so what charge should we give the oxygen? Does everybody see that? Okay. Now, when you do a reaction, you just don't have one of these and one of these. In the pot, when you do the reactions in lab, you have hundreds of them in there, reacting with hundreds of them. So I have another alcohol maybe hanging around doing nothing, methanol. And you see this all happy or not happy? Not happy. So how do you make this O happy? How did we make the O happy before? You see this unhappy O? What made this positive charge go away? The introduction of electrons, right? Now you see that this O is no longer positive. Right? So here we're going to introduce electrons, right? Where are we going to get those electrons? Well, if we can take these 2 and give them only to O, but I said, well, I'm sharing this with H. Can't give them away. So maybe I can get rid of H. So can somebody help me get rid of H? Convince H, hey, leave your electron behind. Give the pair back to O. Yeah, then another alcohol. So this is the second alcohol. This is another alcohol. We're going to do the second one, because I don't want you to confuse it with this. Just one hanging around is going to steal that hydrogen as a proton, and the electrons are left behind. You see, when you have this OH bond, one electron came from oxygen, the other one came from hydrogen. Isn't that true? Now we're asking this hydrogen, hey, Come with me and leave that electron you brought into this union behind. So now this O takes both. Does everybody see that? So we're making CH3, OH, another positive here. But what's the purpose of this? We want to make a neutral molecule. Remember, the product has not yet been made, right? So once this happens, we have CH3, C, H, OH, O. I removed this H already, and I gave the bond to the electrons to O. CH3 over here. I had two from the bottom, and I got another two. So I am here right now. So see if you make sense of all the electronic accounting that I just did. Right, now the reason why I'm coming back to it is because I want you to look at that thing on the board that we just ended up with and tell me where I am here. Well, the square on the board, does it have a carbon in the center and 4 different groups? Yes or no? Take a look at the one on the board. Is there a carbon in the center?
Yeah.
Okay. Does it have an H attached to it? Does it have an R group attached to it?
Yeah.
Does it have an OH group attached to it? Does it have an OR group attached to it? Or an OCH3 group? So what have we made? Hemiacetal. So this is alpha mechanism. Okay, and notice the hemiacetal, is that chiral? You know the word CHIR? The word from 121? Enantiomers, remember all that stuff? Long ago? Chiral is any carbon with how many different groups? 4. So is it chiral? Yes. So it has a chiral center. Alright, now we have to do what? To get to acetal. Because remember this one is what? Unstable, right? Isn't it unstable? So it's not going to hang out like this for very long. So we have to figure out how to get from here to here. Right? So what's the next step? Well, why is this unstable? I told you before. Why is the hemiacetal so unstable? Yes, yeah.
Because the OH could react with the H plus
To give you what?
acetal,
Well,
water.
a leaving group, right?
Yeah,
That's
leaving
water.
water.
So he said, yeah, that OH group has the potential to be a good leaving group, correct? So do we have H plus in the system? Yeah, we're doing this in acid catalyst, right? So we definitely have the H plus. So you can think of this as an H plus floating around, sees the OH, and says, hey, wait a second, we could do this. So now we're adding this to here. Now, I should be making these all equilibrium arrows. So now we have another molecule. That molecule looks like C, H, methyl over here, OCH3, and then this becomes potentially water. And the O takes on a positive charge because what? We had 4 before, and now we only have 2. Loss of ownership. Loss of electrons means positive charge, right? Anytime O has 3 bonds, it's got to get a positive charge, okay? Next, what's the next situation? Well, water obviously has to leave, right? Because this is a potential leaving group. But it's not going to leave unless something kicks it out. Okay? So something has to kick this thing out. What did we say we react with? How many alcohols? 1 we already reacted, that's this guy. And 1 we have yet to react, right? So there's another alcohol involved in this picture yet. Alright, so you see this picture in a square here. Star here. I'm going to continue that. I guess over here. that thing in the star has methyl. So here we are, right? All right, so what's the next step? Well, 2 electrons from this part here. If one of these, right, we need to have a nucleophile to attract. These two can go here. And then these can leave. All right, so let's just go with it for now. Okay, let's see what happens. So, because what made this alcohol react in the beginning, right? Because you know what made the first alcohol react, you know what's going to make the second one react, right? The same thing that attracted the first one is going to attract the second one. The carbonyl attracted the alcohol, isn't that true? But we don't have a carbonyl here, do we? But we're going to make one, okay? So when we do this, we minus water. And now we're going to try to make a fake carbonyl. Did everybody see what we just did? We took 2 electrons from the OCH3, made this carbonyl, and then the water left, minus water. Okay, and why did we do this? Because we need some carbonyl to attract the second alcohol. You know, you've got to get 2 OR groups, right? You can only get 2 OR groups if you have what? 2 alcohols reacting. I only reacted 1 alcohol. I need to react the second alcohol. So right now, I have a carbonyl, right? It looks like a carbonyl, doesn't it? It's positive because O has 3 bonds, right? Does everybody understand? You know, you have to give me, when you do these mechanisms, positive charges, curved arrows, everything I'm doing, you gotta do. Next, now we're going to do the second alcohol. Okay? The second alcohol happens to be methanol again, right? Because we haven't changed anything. Usually they're the same alcohol. And where is it going to attack? Well, if this O is positive, it's going to pull these electrons closer to it, making this carbon very positive, just like before, right? So that makes this attack here. Now, if I'm going to do that, that makes that carbon, the carbonyl, have 5 bonds. Attack means make a bond. So what happens now? Well, these have to move, just like they did last time. So now we have another positive O, but when you gain electrons, this O's positive charge will disappear. So now we have 2 from what we had before, we have methyl, and then we gained another pair of electrons. So far we have this thing. This is a new alcohol that just added right here. Alright, now we're almost there. Well, we can't have a plus charge with oxygen, right? It's not going to stay, it's not happy that way, right? So how did we get rid of the plus charge last time? Remember we had this unhappy plus charge here? An alcohol that was hanging around stole the proton, gave the electrons to O. We have lots of alcohols hanging around. So here's another alcohol just hanging around minding its own business. And then this plus charge O says, geez, if I could find 2 electrons to add to me, but I wish I could get rid of this hydrogen, because the hydrogen is holding one of them. So the second, this hanging around electrons from alcohol react here, steal that H, and these electrons end up going where? Back to O. So finally, this is our product. A carbon in the center, that's this guy, right? Then a methyl group on the left, a hydrogen on the right, OCH3, dot, 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 And then here, we gain these electrons, and we had to, so this O is gonna have 4 electrons that are not bound. And the methyl group. Okay, so OCH3, OCH3, methyl H. We'll come back to this thing, all right? OCH3, OCH3, methyl H. We're done. Okay, so this thing is the acetal. Now, why is that guy so stable? We're not gonna, if there's a third molecule of alcohol, guess what? Nothing's gonna happen, right? First one reacts, second one reacts, third one, who cares? Because what? The acetal is stable, so it's not gonna react. Does everybody get this? So this is your mechanism, your first real mechanism. Step by step. First step, protonation of the carbonyl. Second step, attack of the nucleophile. First alcohol. Third step, removal of a proton, right? Fourth step, that makes hemiacetal. Fourth step, protonation. Right? So this is the fourth step, starting here, right? So we started over here. So we make the fake carbonyl. Then the fifth step would be deprotonation. That is stealing a H. The last step is formation of the acetal. So if you look at this mechanism, if you look at this mechanism in your book, it will be found as 18.4. Okay. So, you know how many mechanisms we're going to have by like next week? Like 30. Okay. So, do you think it's a good idea to memorize this? Never memorize anything in organic chemistry. You're wasting your time. Because once you make a mistake, it's going to be impossible to find the answer or the correct product. So what should you do? Understand every step. Why did this happen? Why did this happen? Right? So we explained it to you step by step, right? The alcohol needs to be reactive with the carbonyl. The carbonyl was reactive, not super reactive, so we activated it. That was the first step. Right? The first alcohol reacted there. Right? Every step has an explanation, right? We needed another carbonyl. We didn't have one, we made a fake one, right? There it is. So you need to instinctively know which molecule is going to attack which. We would never attack a negative with a negative. Likewise, somebody, who it was, I think it was Dodie, right? He said, why doesn't this work? Because, acid doesn't react with acid, right? Somebody asked me a question. Why doesn't, maybe it was you, right? Why does this reaction work? Is an acid reacting with an acid? Acid doesn't react with acid. Acid reacts with base, right? Plus reacts with minus, right? So base doesn't react with base either. So negative, negative don't react. Positive, positive don't react. Only opposites attract. That's reaction. Questions? All right. So when you look at this structure, and you see that if you start with an aldehyde or a ketone, you're making an ether, COC, right? Look at the aldehyde structure. This is the ketone, this is the aldehyde. You see how there's no COC bond there, right? It's a double bond H, double bond R, right? Once you do this reaction, aldehydes and ketones have reacted to make acetals and hemiacetals in the process. You've made this. Once you made this, you made ROC, which is the same as COC, which is the same as an ether, right? ROR is an ether. COC is an ether. That's what you've been naming, right, for your quiz yesterday? So you made one ether in the hemiacetal, and about the acetal, you made how many? 2, right? COC, COC. So we made ethers. And what did I say to you about ethers? Are they stable in acids or bases or both? Now the epoxide reacts with everything, right? So that's a very indiscriminate, that one is not selective at all, right? Because it's so unstable, it reacts with everything. But in general, what do we use ethers for? Solvents, right? Right, remember Grignard THF, that's an ether, right? diethyl ether, dry diethyl ether from the vineyard. So they're usually solvents. And are solvents supposed to react? No, they're supposed to provide a medium for things to react. So ethers are usually very stable things, very stable. So we're making stable things. However, if you have an acid, then the ether will react with the acid, right? Because an acid is H plus, and you have in the ether an O. So that attracts the H plus. So ethers are not going to react if it's base, because O is negative, right? And so is a base. But if there's a positive charge, an ether can be reactive. So we never use ethers as a solvent if you're using acid catalyst. So if you have an acid in the system, you never use ether as a solvent, because the ether will react with the H. You did that, didn't you do that in one of the quiz questions, right? Did we have a quiz question? It says, what's the mechanism, what's the product of this reaction? What is the product of reaction below? And I drew you an ether and HBr, right? So the ether was like something like this, and I asked you to react this with an HBr. Well, HBr is a strong acid, right? Strong acid is always 100% dissociated into H plus Br minus. So what happened? Well, we have the O in the ether being very attracted to the H, right? Because O is negative and H is positive, right? And so therefore, that becomes the protonated ether, right? That's the first step, right? Then what? Then the bromide comes in from behind, right? This is an SN2. And this could be considered the leaving group. And that makes this carbon the attacked carbon. So the bromide attacks the carbon and the leaving group goes away. So we end up with Br, and then ethyl group, right? One carbon here, and then we have like ethene. But then what happens? The H plus from the HBr is attracted to the alcohol. So we make that reaction make a protonated alcohol. Now what? Well, another Br from the other H that reacted is going to attack here, and then that leaving group goes away. So we make another ethyl bromide. So how many ethyl bromides did we make? Two. Did we make any alcohol? Yeah, in the process, but it doesn't hang around for very long. The product is going to be only ethyl bromide. So this is proving to you that you can, if you want to use this as a solvent, you cannot, because this is an acid, will react with ether. Acid always reacts with ether. So you cannot use ether as a solvent if your reaction is acid catalyzed. Questions? All right, there are other reactions that we have to do, 18.5 and 6. So we've done this 18.4. Let's talk about protecting groups. I'm going to skip the protecting groups, okay? Because normally during the semester, it's a hard enough topic, so I don't think we have time to go into the nuances. But I will tell you this, that when we, you might say, well, why are we doing all this sugar chemistry? Okay, so let's go back to the sugars. I don't know if you learned this in biochem, but you see these structures, they are interchangeable. You ever hear the word epimers? E-P-I-M-E-R-S, epimers. Or the alpha and the beta version of the sugar, alpha sugar, beta sugar. These guys are interconvertible. What does that mean? That sometimes the ring closes, sorry, this straight, this is like a skeleton, right, of a fish or something, right? So this straight chain thing closes to make the ring. And sometimes the ring breaks open and makes the skeleton. This is happening back and forth, back and forth. Straight chain, closes up, makes ring, ring breaks open, makes skeleton, skeleton breaks ring, it goes back and forth. This is an equilibrium, it's happening like that. So the stable form is this one. But this one is a close competitor, it's like 60-40%. The reason why the straight chain closes and makes a ring is because you have an aldehyde here. And what is attacking this aldehyde? Well, look at the ring. How many members in this ring? 6, right? 1 oxygen, and then 2, 3, 4, 5, 6-membered ring. 5 of those members are carbons, 1 is an oxygen in the ring. True? So, you see this carbon? That's 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and this O from the OH is the O that you will find here. So how did this happen? Well, this OH, which is an alcohol, sees this aldehyde over here, and this OH, like a snake biting its tail, let's say this is the tail, attacks the head, carbon 1, and makes a ring. See, now we have a big ring. If this OH over here attacks the front, we make a ring. Who's not invited to the party? Who's not in the ring? This part, CH2OH. That guy is not involved. So you see how CH2OH over here is outside the ring? So this is how the ring is made. Well, why does it happen, you might say? Well, because the aldehyde is reacting with 1 alcohol, and we make hemiacetal. Where's the hemiacetal? You see this guy here? This carbon where my cursor is? What does it take to have a hemiacetal? You have to have an R, an H, an OR, and an OH. Those are the 4 groups. So you look here and you say, well, here this carbon has an R, that's this whole thing, this carbon, an H, an OR, or an OC, and an OH. So this carbon right here where the cursor is, that's the hemiacetal. Does everybody see that? So this is like a ring coming from a snake biting its tail, okay? Except that this part of the tail, this last carbon, is not in the ring. So it's O attacks aldehyde C. So this is 1 O, that's this O. 2, 3, 4, 5, 6-membered ring. 6-membered ring, 5-membered ring. Those are the most stable in organic chemistry. So that's why we make, you see this one's a 5-membered ring, this one's a 6-membered ring. We're not going to make 4, we're not going to make 7, those are not stable. So when a sugar cyclizes or makes a ring, it's the same reaction we just studied. Nucleophilic attack, acetal formation, right? In this case, hemiacetal formation. Now, do you think this guy is stable or unstable? Well, it's not stable, right? Because it's a hemiacetal. That's why it opens up and makes a straight chain. Then it reacts again, makes a ring. Then it's unstable and breaks open and makes a straight chain. Do you understand that this equilibrium of back and forth? The reason why, if this was a stable ring, would it open up? Think about the epoxide. The epoxide is very unstable, right? The first thing it wants to do is open up, right? So unstable rings want to open up. Even though this is a 6-membered ring, this hemiacetal is not stable. Why? Because of the OH being the potential leading. So therefore, it opens up. So it's doing this back and forth, back and forth, back and forth. This is glucose. It could be mannose. It doesn't matter. These are monosaccharides. Mono means 1 sugar. Okay? Now, what do you see here? 2 sugars, right? Every time you see a ring, that's a sugar. Okay? So here's like a glucose, right? 6-membered ring. This is identical to this one. And what do you notice? That the O that used to be the O here, that's this guy here, this used to be the hemiacetal carbon, but now the OH is gone. You see there's no OH attached to this carbon where my cursor is? So therefore, this is acetal. It is stable, right? And, I'm sorry, not this, they shouldn't use this thing. Acetal they wrote here, but really the acetal is here. I don't know why it's, I kind of got thrown off myself. This, so in your mind, you see this acetal, they put it there, but it's for the whole molecule. But this, you see where my cursor is? That's, this carbon here is this carbon here, right here. So what does an acetal have? Well, an acetal has two OR groups, or OC, COC, COC, RH. Then come back here. C is where I have my cursor, OC, C, O, O is here, C, so this is COC, COC, R is this whole thing, carbon, and then H. So this is where my cursor is, make sure that you understand it's not here. I don't know why they circled this is wrong. I just got this off the web, this is not mine, but I want to correct it now that I see it. So this guy here is the hemiacetal, is the acetal. Glucosylpeptide, another sugar, right? So this sugar comes from fructose. So this is glucose plus fructose makes sucrose. Sucrose is table sugar. So when you have this on your table or you have this in your kitchen, this is a stable bond. The acetal is stable. So therefore the sugar will stay in a ring. It's not going to open and close, open and close. That doesn't happen in sugar. Okay? So sugar is an acetal, therefore it doesn't open and close. Glucose is a hemiacetal, so it opens and closes all the time. Glucose plus glucose gives you maltose. Glucose plus fructose gives you sucrose, like this guy. And glucose plus galactose gives you lactose, like lactose intolerant people. So that's how you make these sugars. You keep making this reaction happen. Every time you have one sugar, you react with another guy, you make an acetal. This is this reaction that we just learned, this mechanism. Okay? So that's why it's important. That's why you have to know it. That's why you're going to make you learn it. And you'll see it on the MCATs, you'll see it in any kind of biochemical test.
So for the alpha and beta glucose, how does the OH move up and down?
Oh, you have to open it up. So for glucose, alpha, beta, you see how this is unstable? This is the heavy acetal. So this OH, if it closes and the OH is up, it's called beta. But if it closes and the OH ends up down, because once you're in this form, you can rotate, right? This is a spinning thing, like a propeller. So sometimes when you close the ring, the OH ends up up. Sometimes when you close the ring, the OH ends up pointing down and this H points up.
So just the rotation.
Yeah, so 66% or 65% of the time it's beta and 35% it's alpha. But if the OH is up, it's beta. If the OH is down, it's alpha. But that's beyond the scope. So you don't need to know that so much. That's more of a biochemical. But yes, that's a good question. So that's what we call epimers. Questions about sugars in general? So you have to know because it's a biochemical reaction, right? So it's 10:25. I'm probably going to do this reaction here and this reaction here. Amines and enamines, because we did the DNP reactions and semi-carbazole reactions. I have to show you what that reaction is. I need to do the Wittig, and that's the end of this chapter. So probably we're going to take a little break. I'm going to come back and give you homework to do for this test that's coming up.